I'll show you now a general strategy for solving second-order transient circuit. These are circuits that contains two energy storage elements that cannot be combined. In general, what I do is I write a differential equation that describes the whole circuits, and typically, since it's have two storage elements that cannot be combined, it will be a second-order differential equation. It contains the second derivative, the first derivative, and the actual function. And typically, I write it in such a way the coefficient for the highest, which is the second derivative, is just simply 1, and whatever is the derivative or the coefficient for the first derivative will be 2 alpha, and the one for the actual function will be omega 0 squared, and that will be equal to a forcing function. This forcing function could be 0, it could be any other number. And the solution in that case is simply two parts, a particular solution and a complementary solution. So the particular solution depends on the type of forcing function. In the case of DC, which is what we're dealing with at this point, it will be just simply another constant, and that constant can be easily computed using this equation. I'm assuming that f of t is just simply a. You can just say, well, if this is a, this will be 0, this will be 0, and the x of t is just simply a divided by omega 0. Okay, and that will be the particular solution. Next, what we do is we derive what we call the characteristic equation or the auxiliary equation. And again, if we write the differential equation in such a way that the coefficient of the highest and second derivative is just 1, it's simple to get the characteristic equation. That simply will be s squared, that's 1 in here because 1 in here, and there will be 2 alpha in here, 2 alpha times s, and that will be omega 0, and that equals 0. So we do then, and you compute the discriminant of this one here, delta, which is just simply b squared, which is 2 alpha squared minus 4 times 1 times omega 0 squared. Okay, so you compute that discriminant, and based on the value of that discriminant, you'll end up with 3 different response shapes. And these, basically, you can either compute the discriminant or you can basically take a look at the alphas and omega 0. They're the same. In that particular case, where delta happened to be a positive number, we get what we call the overdamped response. And of course, S1 and S2, since delta or the discriminant is greater than 0, there will be real and distinct. If it's an underdamped, that means this delta here happened to be less than 0. That means the solution in here for S1 and S2 are simply S1 and S2 will be complex conjugate. And when delta is exactly 0, we get what we call the critically damped response, and we have the same S1 and S2, and that will be just simply negative alpha. And once you figure out that, okay, and you figure out the complementary solution, you just add it to the particular solution you found earlier, and you get the final solution. And just as a quick reminder, where the overdamped and underdamped and critically damped, here's a different solution. Again, these are based on the value of alpha and omega 0, or the discriminant of the auxiliary solution, or the auxiliary equation, or the characteristic equation. So what we have is, in the overdamped response, S1 and S2 are real and distinct, versus in the underdamped, there will be complex conjugate, and in critical damped, there will be alpha is real duplicate. That's what we have. We have only one in here. It's a duplicate. So in the overdamped case, what we have is the solution will be a particular solution plus k1 e to the power s1 e to the power s2 times k2 in here. And then we use two initial conditions to compute what that k1 and k2 are. First, we substitute t equals 0. We'll end up with this equation in here. Second, what we do is we take the derivative of this equation and we substitute t equals 0 for that derivative, and it will be equal to k1 s1 plus k2 s2. In the underdamped response case, what we have is we have the following in here. The solution will be, well, first you compute what omega d is, which is just simply the square root of omega 0 minus alpha 0. Okay, and the reason why is because we're not going to be using S1 and S2. You don't not need to compute what these complex conjugates are, because we're not going to be using them. What you end up with is the particular solution that you found earlier, times e to the negative alpha. We know what alpha is. Well, omega d, we just computed its cosine and sine. Remember, an underdamped has some sort of an oscillation, a damped oscillation because it has a cosine and sine. And then we use two initial conditions to figure out what beta 1 and beta 2 are, and these are exactly when t equals 0, and then you take the derivative of this one here, and you substitute t equals 0 in here, and you get these two equations. You solve them, you get beta 1 and beta 2, you substitute them, you get the complete answer. And in the last case, when it's a critically damped, what we have, you can definitely compute the solution for S1 and S2, and you're going to end up with negative alpha. But the solution is of this form. It's k1 S1 of t, k2 t. There's a t in here. Let me just make sure I highlight it in red in here. There's an additional t compared to this solution here that doesn't have that t. Okay, and then again, use two initial conditions to find what K1 and K2. That's simply when T is 0 is basically that. Well, and then you take the derivative of this equation and you set it to T0, and that's basically in here.